questions. We'll work through the ones that are in the chat as well, in reverse order they were asked. So I like this question. I like this question a lot. It's basically HBr, two equivalents of HBr gives you product A, and then a base gives you product B. I am not recording, so I will start recording. Shit. No, it's somebody is recording. Thank you, whoever is recording this meeting. Please keep recording. Don't change anything. Okay, so we have a question like this. Then, so you should take it part by part. We're actually saying, hey, you get an intermediate, hey, you get a product. I guess it does depend. Let's just say it's one equivalent. I think that's what I meant by the question as well. Deprotonate using H, then attack with the BR. Actually, Alyssa, we're going to answer that question with this question. So a triple bond acts like a double bond. If this was a double bond, you would add HBr Markovnikov. If it's a triple bond, you add HBr Markovnikov. It's no different. So you'd add a positive charge here, and you would have an H here. You'd have two H's. Then Br minus is a nucleophile, attacks the carbocation. So of course we get the carbocation there and not the other site because you have a secondary versus a primary. We treat this with HBr. Now, not only is it secondary, it also has resonance from the bromine that can donate in. And so, of course, we are going to generate this guy. And that's going to react with the Br minus. To stick two Brs on there. No further reaction can occur. We've basically saturated all the double bonds with Br, HBr. We're done. Now we add a strong base. We note it's a Zaitsev base, not a Hoffman base. It's not one of the big bulky ones. It's one of the smaller ones, but still definitely basic and not nucleophilic. It's not stick-like. It's definitely a ball. And so if I'm looking at this, I'm thinking there's my leaving group, or that one, could be either one. And there's a hydrogen on a more substituted carbon next to that. And so I would expect my base to deprotonate. To give me that. Now I can't do a second deprotonation because there's no other proton on that site. Yeah, sorry, two equivalents underneath the arrow, an isopropanol underneath the other arrow. And I can no longer write because I exited. equivalent. And that says isopropanol. So that's our product. So Alyssa just posted a question in the chat, which is very closely related, where she asked, what is the product of this? Well, that's this. Sodium hydride is always a base. There's a leaving group. There is an acidic proton. The acidic proton is 180 degrees away from the leaving group. It is antiperiplanar. We have a nucleophilic. We have an acid-base attack, displacement of the bromide, synthesis of the triple bond. Can I make a double bond with a terminal methyl? It's really hard to do, Melitza. So I think I would define it as one equivalent in the future. I don't think I was completely clear in the question, but no, you can't really. You're not going to make a ketene, which is a carbon making two double bonds on both sides. Okay. So if I jump back up to Alyssa's question, if I could explain the difference between a base and a nucleophile again. So bases are basically subsets of nucleophiles. Like, what is a nucleophile? It has to be electron rich because it's going to need to donate 2 electrons. That is what a nucleophile is. That's kind of the definition. What is a base? It's a nucleophile that donates 2 electrons to a hydrogen. So a nucleophile donates 2 electrons to a nucleus. A base is a nucleophile that does it to a hydrogen. So bases are subsets of nucleophiles where the electrophile is a hydrogen rather than any other atom. In 90% of the case, 99% of the case in this course, a nucleophile attacks a carbon, a base attacks a hydrogen. But I am going to say that nucleophiles can attack other atoms. They're not restricted to carbon. It's just we've been focusing on carbon. Whereas a base always attacks a hydrogen. And so it's kind of a specific subset. So every base is a nucleophile. Every nucleophile can potentially be a base. Because it's all about what is the atom that you are targeting. That's all. That's what this is all about. So let's say, why would something be a nucleophile or a base? Well, it all comes out to whether it prefers to attack a carbon or a hydrogen. And how do we figure that out? Well, normally there's much more benefit. There's a much more energetic benefit for attacking a carbon. You make much more stable molecules with nucleophiles attacking carbon. So if you have a leaving group on a carbon, whatever your nucleophile is probably going to be more stable making a bond to the carbon than making a bond to a hydrogen. But sterics get in the way. So if you have a bulky, negatively charged or electron-rich functionality, it is far less likely to be a nucleophile than a base, because to be a nucleophile, you need to attack the carbon antiperiplanar to the leaving group to do an SN2, or you need to attack the carbon lone empty p orbital in an SN1. Whereas to be a base, all you need to do is touch the surface of the molecule and strip a hydrogen off. That's a lot easier than trying to navigate your way to attack a carbon that is deep within the molecule. So that's why I make so much emphasis on to add an extra carbon. I don't believe so. Oh, over here. Yes, I did. With hydrogen to an Sn2 because its Tic-like does the basicity dominate. So, yeah, sodium hydride is a weird one because all the rules, if you talk about the shape of the nucleophile, go, that's a nucleophile. It's small, it's tiny. You can't get smaller than H minus, but it's always a base. And no, I don't understand that either. I don't know why sodium hydride is a base. Nope. I honestly, I do not understand. And I have seen discussions where we get into charge densities around things and orbital overlap calculations using quite high advanced density functional theory. And it all comes out convincing me that it's a base. I do not understand what is going on because it's small. It should be in file. And when it's in the form of sodium borohydride, it is a nucleophile. And to me, sodium borohydride is bigger than sodium hydride. So I would expect, if anything, sodium borohydride would be a base and sodium hydride would be a nucleophile, but it's backwards. So compared to all the rules I say about size and all that mattering, the hydrogen goes backwards. Because if it made sense, this wouldn't be organic chemistry. And I don't, it's got something to do with quantum. And that's as far as I can go. I don't actually understand. I'd be lying if I said I understand why sodium hydride is a base and sodium borohydride is a nucleophile. Victoria asked, if you have acid in water, do you take the H plus from acid or from the H2O plus that forms when acid is in water? I'm happy with you doing either. Technically, Victoria, you're absolutely right. Any strong acid is going to dissociate and you're going to generate H3O plus. You're not going to strip an acid from H2SO4 and water. You're going to strip it from the hydronium that forms from H2SO4 plus water, generating H3O plus, and that's going to be your acid. I don't care. It's H plus. It's there. Fine. Is the final exam cumulative? Yes, absolutely. Okay. So let's do a question like this. AIBN heat and is this one of my assignments, Guntas? If so, which one? Oh, you made it up. how about I come back to this, because I want to ask you this. There's a bunch of complex. I'm looking at this and going like, I really hope I didn't ask that question. So I'm going to put a line under this for now, and I will come back to it because there's a bunch of complexities to that question, which there's a few things that can go on. So let's talk about Madison's question, because I think Aurora popped it up and said, yeah, I'm interested in this too. I'm not going to write your name, Madison. You got to buy. So what I think they're asking is E1 versus Sn1, E2 versus Sn2. So why would we do, what are the differences on these? So in general, and I think this is the right question. In general, E1s and Sn1s compete, E2s and Sn2s complete. Because in both of these cases, must generate carbocation. That's common. So in both cases, you've generated the carbocation. You have convinced yourself that the electrophile can lose the leaving group and form a stable carbocation, whether that be tertiary, resonance stabilized, or maybe secondary because there's no other option. And then what causes an E1 versus an Sn1? Well, this comes down to the sterics of the nucleophile and the availability of adjacent hydrogens. So if you have a case where you have no alpha protons, for example, what do I mean by that? Well, let's say we had a case where we had a molecule like this. Obviously, iodine is the best leaving group. There are no protons alpha to that carbon. So you can't do an elimination. It's not possible. There's no possible elimination. There's no possible hydrogen to remove, and elimination is impossible. I don't know how many ways to say that. So if there are no alpha protons, you're definitely going to do an Sn1. How often does that happen? Not often. That is really rare. More often, what we're looking at is small nucleophile. I was going to write shitty base, but I'll write poor quality base and just say shitty base. So if what you have as your nucleophile is a really poor base. What do I mean by a really poor base? Thiols tend to be bad bases. Cyanides, azides, these all are bad bases. They're much more likely to be nucleophilic than basic. Whereas an E1, large nucleophile. So if your nucleophile is large, then you're far more likely to do an E1 because it's much less likely to be able to get to the carbon because the carbon is hindered by all the adjacent carbons. And then that your carbon, your positive charge is on tertiary, makes it slightly more likely for an E1, although tertiaries are still very, very possible for Sn1. So maybe not that useful. And if you're going to generate the new double bond you're going to generate with the E1 is going to be in conjugation with another double bond, that really favors the E1 over the Sn1, because then your double bonds are going to be in conjugation with each other. That is massively stabilizing. But you can see the big difference here is the size of the nucleophile. Small nucleophiles are more likely to do Sn1, large ones are more likely to do E1. And unsurprisingly, we see the same thing with the E2 and Sn2. Large bases tend to favor E2. Small nucleophiles favor the Sn2. You need a hydrogen that can be antiperiplanar to the leaving group. So it needs to be able to rotate to be antiperiplanar. In an acyclic molecule, a molecule without rings, when the leaving group is not in a ring, this is never a problem. If the adjacent carbon has hydrogens, you're fine. If the leaving group is in a ring, sorry, my sleepy period of the day, then you need to have a hydrogen that is antiperiplanar to the leaving group. That can be trickier. It's not guaranteed. Now, in the Sn2, needs to not be tertiary. If it's tertiary, no Sn2 for you. I'm going to put a small caveat on that. As illegible. Unless it's not clear. If you can make a ring and the leaving group is tertiary, that is possible because it is tied together. It's going to eventually hit. But in 99% of cases, if you have a tertiary leaving group, you are not going to get an Sn2. You're going to get the E2. If you have a primary leaving group, the Sn2 loves it. So tertiaries are almost verboten. They almost never go E2 because the leaving is very available, and generally a nucleophile can get into on that carbon and make the attack, unless the nucleophile is particularly bulky. So again, so this is a really unsatisfying answer, because I'm basically saying you need to weigh multiple parameters in all these cases. And the truth is that's the answer. Like, the answer is you need to weigh multiple parameters in all these cases, not cut and dried. Okay, so as I'm looking at some of the other questions on to kind of address this one. I'm going to just actually start with Alyssa's question, which is, what the hell is going on the right-hand side of this page? So I'm going to ask the audience here if they can help me out. So the top molecule is LDA. If you take a look at the chat, you can see at 1:53 p.m. Alyssa posted a question. Ah, shit, I glitched. I have no idea what I just said in Madison. You have to balance things. It's tough. Boo-hoo. So carrying on Alyssa's question, 1:53 p.m. she posted a question. Take a look. What the hell is going on the right-hand side of the page? And this is what she's got. So we have this molecule reacting first with LDA, and then with this ketone. LDA deprotonates hydrogen. Absolutely. LDA is a very strong base. This hydrogen is very acidic because it's on an alkyne. Thank you, Dea. So what's that going to do with a ketone? Perfect. Nucleophilic attack on a carbonyl. Now, these are really good, right? Because triple bonds are really small. So this is really like an ideal carbon nucleophile. So we get that product. Then we treat that with water. And we just protonate. Clean up our charge. Amanda said, isn't that a valid Lewis structure? Why is it in brackets? It is valid. I'm just indicating that it's temporary. It doesn't need to be in brackets. I'm going to erase the brackets. I'm probably overkilling. You're right, Amanda. It is perfectly valid. There's no reason for it to be in brackets. Brackets say this is temporary. It's definitely temporary, but it is a valid Lewis structure. Okay. I glitched then. So what I was saying is primary leaving groups favor SN2s. And that's because primary leaving groups are very accessible because they're on the end of an atom, end of a carbon chain. There's not a lot of steric bulk near a primary leaving group that favors SN2. And then I went on to say that I wish this was easier. I do, because then I would actually be able to figure out what the hell my reactions are going to do in the lab. But it's not. In a lot of these cases, we're balancing multiple factors, some of which contravene each other. And we need to kind of figure out what's more likely under the circumstances, taking all these different components into account. Okay, blah, blah, blah. Olivia telling me I'm not that useful. You're absolutely right, Olivia. Is the exam open book? Yes. Mostly because I can't think of a way that I could do a closed book when it's remote. Or rather, any of the proctoring tools that are available to me that do a closed book freak me the fuck out. Can I review how to do stereochemistry in E2 reactions or Sn2, Victoria, or both? Coming back to you now. Oh, wow, that doesn't explode in a minute. Both, okay. Great question. Dea, can I go over epoxy openings under different conditions? I think, actually, if you look at the office hours I posted to YouTube from Monday after class, I did go over that. So I recommend taking a look at that. So just due to time, I'm going to pass on that question. Do we lose a lot of marks if we don't indicate transition states on the exam? Stephen, if I ask you to indicate the transition state in a question and you don't, then you will lose a lot of marks. If I ask you to draw the mechanism for a question, you never need, if you draw a mechanism, you never need to draw transition states. You're just drawing intermediates one after the other and arrows showing how one intermediate gets to the next. So you would not lose any marks if I ask you for the mechanism, you don't show me a transition state. If you draw the wrong intermediate because you don't understand the transition state, then you drew the wrong intermediate and you will lose marks. And your definition of a lot and my definition of a lot might be different, and so I don't care to entertain that conversation. So water and what else can make the molecule neutral does depend on what we're working with. Often, water and any alcohol can neutralize things. Think of oxygen hydrogen bonds as being your bank. You can deposit, you can withdraw hydrogens from it. So if you need to make something neutral, sure, pull the hydrogen off of water. If you need to make something neutral from being acidic, like being positively charged oxygen or nitrogen or sulfur or whatever, put a hydrogen onto water. Water's your general friend for making things neutral. Any alcohol can also do this. So methanol, isopropanol, ethanol will also be able to neutralize things by moving protons around. Lauren's question, this might be a stupid question. When do you know if there's water when there's not water in reaction if it's not given the reaction conditions reagent? I think on an exam I'm quite happy to state this, always assume aqueous workup unless otherwise stated. And maybe I'll put that on the front page. So assume that there's water added to the reaction at the end of the reaction to make things neutral. So I will probably explicitly state when there isn't water present. Like, you know, there's an immediate reaction right afterwards, and I say no workup. How many questions will there be on the exam? I have no fucking clue. Do you have 4 hours for the exam? You've got 3 hours for the exam. You have half an hour to upload your answer. Because, look, the exam's on the 11th. That's my anniversary. My wife is going to murder me. If and I think our exam starts at some ungodly hour. It's like 8:30 in the morning, isn't it? And so 3.5 hours takes us to noon. And she's pregnant and she can't eat meals late at night. So I need to take her out for lunch on the anniversary. And so I need to go into the county for this. And I can push lunch to about 1:30, otherwise she'll get hangry. So you have 3.5 hours. Those of you who have extra time have extra time. There aren't many, and it'll be monitored by a GA. It's at noon? Oh, fuck. I thought it was 8 a.m. Okay, well then, I better write a perfect exam. So I'll figure it out. It's at noon. That makes a lot more sense. I'm really glad for you guys it's not 8 a.m. For some reason I thought it was 8 a.m. Okay. Was the last question E1 or 2 because it was a strong base, but you made a carbocation? I made no carbocation in this example. There is no carbocation in this example. Nice try, Mahfoud. I'm not allowed to move the exam. I have no rights over the exam. The exam is actually, final exams are actually, like midterms I can do whatever the hell I want. Final exams are actually legal contracts with the province of Ontario. And so I cannot move a final exam. I actually have very little power over final exams. Yeah, it'll be printed out in write format. It will be exactly identical to the midterm in terms of the format. Alyssa, I've got 10 minutes, so I'm going to go no, but I am going to happily do LCAO if somebody came into office hours and said, I really have a specific example that I want to cover, and I will then record that and we will post it. My wife is not a morning person, Madeline. It's a great idea. I get up bright and early with the birdies, or before the birdies. I get up bright and early with my border collie, but she sleeps in. Yes, Kate's, yeah, I think that's fair. We'd say your colleagues have already made the point that it starts at noon. I agree with them. Maybe you're just on delay. I do like the mix of relationship advice and evidence of the timing of the exam. Okay, can I do a retrosynthesis example? Let's finish with a retrosynthesis example. Okay. Here's the question. Make the guy on the left from the guy on the right. Oh, Christian, I think Alyssa is wondering if you'll ask us on exam to talk about how a mechanism works using LCAO. I might ask. I could maybe ask you that about an E2 reaction. I'm going to say no. And the reason I'm going to say no is because it would take you a long time to write out that answer. Now, will you need to do a form of that in your head to figure it out? Abso-fucking-lutely. Will you need to draw it out? No. It just takes too long to draw. There's just too many things to go in. But do you need to know that E2 is an antiperiplanar? Yep. Is there any way to explain that without considering the antibonding orbital of the leaving group? Absolutely not. Or, well, there is. If you just go, I need to memorize that they're antiperiplanar, that works just fine. But it comes from that. So will I ask you to draw it? No, I won't. I think that's unfair. I think it's kind of advanced. I just like sharing it because it's why, and I like saying why. Okay, any ideas on what to do here? I'm going to say when in doubt, number your fucking carbons, number your atoms, figure out what's attached to what bonds you need to make. Always a really good start. As I desperately look at this and figure out how I've messed this up and made this impossible, but I haven't. It's okay. This does work with the chemistry you covered. Any suggestions? Well, so Olivia's saying we need to break the ring. Retrosynthetically, we need to break the ring. Synthetically, we need to form the ring. Absolutely. So which way would you open a ring up with OH at the end? So where do you want the OH? Do you want the OH attached to 1 or do you want the OH attached to 5? Faith is going 1. Hannah's going 5. So what I'm going to say is you could do either. There are 2 ways to answer this question. They are both fine. So, yeah, so so you guys are, you might break into 2 groups who see this differently, and both you are right. You can get to the answer from either side. Personally, I was attaching it to 5, but I immediately see that it can be attached to 1 too. So what we can say is this comes directly from. So what we're going to do is introduce this idea called a synthon. I'm not going to say what the leaving group is. I'm just going to say there's a leaving group at 5. Conveniently, that could be iodine. So a synthon is something where I'm kind of representing symbolically and kind of in the abstract what I need. I need to make a bond between the OH on carbon 1 and carbon 5. So carbon 5 is a leaving group. I don't give a shit what the leaving group is. It just needs to be a leaving group. My phone is going to say it does not understand what I'm saying. I didn't understand that. Yeah. Hopefully you understood better than my phone. So I don't care what the leaving group is on 5. Fortunately, I've got an iodine there, so I've got it. Alyssa, I can go either way. So there will almost certainly network question. I give you those boxes and you fill in reagents and products. You need to think things through. There will almost certainly be at least a question like this, where you need to propose multiple steps and multiple sets of reagents to get from A to B. And it will probably be phrased as provide a retrosynthesis and a synthesis of the following transformation. And I'll give you, make this from this, like this. And you need to provide a retrosynthesis and a forward synthesis. So you will almost certainly get both questions, both a network question saying fill in the blanks, and a question like this, which is create the entire thing de novo. This is both terrifying and kind of the point of everything. I can't tell if you're being sarcastic, Alyssa. I love these. And if you're not being sarcastic, just do not share your address or people will chase you down. Well, they can make good assignment questions, but the problem is the answers for these kind of questions wouldn't be very good assignment answers, because I would put out an answer and it would be one possible answer, and there are 1,000 other possible answers, and then I will get a whole bunch of emails going, well, why isn't my answer the answer that you gave me? And my answer would be, your answer is fine, it's just not the one I gave, because there are a lot of possible answers. And then I just get depressed. Okay. Can somebody take me from the structure on the bottom left up to the structure on the top right? You can do this in one step if the leaving group is iodine. So how do I go from here to here? I agree, Jesse. For me, actually, what put me on this train was sitting in a class on this after a long series of classes in molecular biology I was taking at the same time, where it was memorize this cycle, memorize that cycle, memorize the other cycle. And then it was a class where it was like, here, solve some puzzles. And I went, holy shit, I can get paid to solve puzzles for a living. I'm doing that. Well, no, we want to go from the double bond to this. So we're saying this comes from that. This is what this arrow means, is comes from. We're trying to go from this to this in a forward way. So we don't want to make it double bond. We want to break a double bond. So Faith suggests H plus in water. If we're anti-Markov then. Exactly, like Olivia, exactly. It's the opposite. Hannah said and water. Christian said some sort of anti-Markov. So we need to an anti-Markov addition of water. How the fuck do you do that? What are your reagents? You all know this. You're all right. It's anti-Markov addition of water. Nope, that's for. There we go, Dea. Close. Samantha in for the win. BH3, sodium hydroxide, hydrogen peroxide. AIBN heat and water doesn't actually work. I wish it did, Jesse. It doesn't. That works for the HBRs and halogens, but you can't generate the oxygen. OH is a shitty ass radical. You don't generate that. It's not a halogen. So it'd be really nice if anti-Markov additions of water follow the same way the halogens don't do, but they don't because oxygen's not a halogen. I don't make the rules. Okay, that's perfect. So this is one way, but those who are saying, look, attach it to 5, then what we need, if we attach it to 5 instead of 1, is we need a leaving group at 1, right? Because then we treat that with the base. And this would cyclize to make the 6-membered ring. So any suggestions on how to get this back to the green structure? Or how we would either way turn this into green or turn green into this? Well, That would yeah, so we got a base to turn this into the product. But how do we go back? Yeah, no, absolutely. That's how we turn this into the product, is Sn2. But how do we get to this molecule from this molecule? Because if I'm trying to get back to this molecule, this is my starting material, this is not the same thing as that green molecule. Both Dan and Samantha answered how to turn it into the product, but not how to get back towards the starting material from there. And you're both absolutely right. That's exactly how you turn that into the product. So what we've done is we've reduced the question from the original question to a new question, which is that. So you've ripped open a ring. Good. The good freedom you got is you can define that leaving group as anything you want. So let's say it's a bromide. And if I did an anti-Markovnikov addition of bromide, I would install bromide at that position. Yeah, perfect, Jesse. Oh, you spelled it right. Your Russian is very good. And if we want to go from here to here, this wouldn't work great in reality, but there's actually better ways to do it. But let's just keep it simple. We could use a small nucleophile like sodium hydroxide, which would do a nucleophilic attack that's a primary leaving group. It looks good. So double bond wouldn't be in conjugation with the other double bond. So we can do a primary nucleophile, small nucleophile, displaces the I generates that intermediate product with the double bond. Then we get rid of the double bond with AI band HBr. We get this leaving group OH thing, and then we can treat that with the base. We can close the ring and get our product. Can I use HI instead? Absolutely, you can use HI instead. You can use HCl instead. They're all the same. With the AIBN is what Hannah's asking. So which of these answers is better, the one in blue or the one I drew first in red? Honestly, I saw the one in blue first, but the one in red is better. But both are absolutely full marks. They're both correct. They will both get you back to that starting material. The red one is just shorter. It's only got one intermediate, whereas the one we drew in blue has two intermediates. And you always want to minimize the number of steps you need to use. Okay, I'm going to leave it there for today. It's Wednesday. After class on, no, it's not. It's Monday. Holy shit. I have no idea what day of the week it is. Office hours tomorrow at 10 a.m. And then I will be holding a special office hours after class on Friday. Sorry, I'll be holding a special office hours during the class time on Friday. There's no class on Friday because we're done. I'm not sure where to go for practice for these. Any suggestions? The textbook, I think, has a few. So the end of chapter problems. The issue here is there's no way to practice these unless I just can't give a million answer keys. So I can give a lot of problems, give a single solution, but the problem then is that your solution might differ from my solution. Your solution might be completely valid. So I'm loath to give too much. What I would say is, I think as you familiarize yourself with the reactions, you'll find this easier and easier. I promise not to make them too hard. Anything you'd see will be about a maximum difficulty with the kind of difficulties that we're seeing here. Like 2 steps. You do 2 different things. But really what we're trying to do is we're trying to position functional groups in the spots we want them. Like last class, we finished with an example where we had to move a double bond around. We'll do another one next class, I promise. And what we did was we just try to think, okay, where do I want to move the functionality so I can turn this armature into the product? Which bonds do I need to break? What bonds do I need to break? And what does that mean for the atoms that I need to make the bonds between? What do I need to do to them to make this doable? So there are a few examples at the end of chapter problems in a text. But I agree, not as many as I'd like. Okay. How do we open up the ring originally? Gabrielle asked. We didn't open up the ring, we closed the ring. The synthesis is going forward. The synthesis is going from right to left. I opened up the ring because because what I'm essentially saying is I can close the ring using a nucleophilic Sn2. I didn't open the ring, I closed the ring, but to go backwards, I need to open it because that's what going backwards in time means. Amanda, I think there's a few examples in assignment 5 where I have a couple of steps. I'm going to pull my assignment 5. No, assignment 5 is all just network questions. You're right, I don't have any questions like that in my assignments. Let me think about that. I'll see if I can post some options tomorrow. It's a little bit close to the exam for me to be posting more material, but that's fair. Yeah, Alyssa, yes. The exam's not hard if you practice for it. No, there won't be no answer keys posted for the practice exams. Okay. I'm gonna think about it, Amanda. I'll see if I can maybe post a couple of examples to work through. But the whole thing is just, I find that when I post the answer keys to things with multiple answers, it freaks people out more than it soothes them. So maybe I post some practices to do, but not necessarily answers to them, because As the question gets even remotely complex, the number of possible answers expands exponentially. And so everyone's answer is going to be different. Okay, take care, everybody. Have a really good day.